let us learn. Hopefully your break was good. It feels weird to be back, but we only have like 3 sections left of curriculum. We'll finish that this week, and then we got 2 weeks after this week to review. So after we finish curriculum, like next week, I'll keep coming in here, and you can choose to come in here or not, so that we can do BC specific review, like all your integral stuff, all your Unit 9 stuff, all your Unit 10 stuff. We can try to review it in those 2 weeks. Yeah, let me just leave it at that. I got more to say about what we can do in the coming weeks, but I don't want to overwhelm you first thing being back. But here's what I thought we'd do today is, remember I said I'd give you a sheet with all the convergence tests that you've learned. I thought today would be a natural day to go through that because like you've been out for a while, you may not remember this. So we'll go through this, then we'll start 10.6, which doesn't so much have to do with convergence, but a new idea. The whole reason we're doing series is kind of what we're going to learn in 10.6. But okay, watch this. Here's all the tests you have for convergence. Let's see how much you guys remember. And then that way you have it for homework and all that stuff. So geometric series, they're the ones that look like this, number times ratio to the nth power. And that converges if and only if, do you guys remember what needs to happen?
R is less than 1.
Yeah, that's the thing, is that if R is less than 1, then this will converge. Okay, I was going to say R is less than 1 just for convenience, but really you could treat it like absolute value of R is less than 1, because then that would include alternating series. But let's just keep it simple and say R is less than 1. Then to say that the series converges to the value, this I would be impressed if you remembered. But like if you add all these to infinity, do you guys remember the formula for what that converges to? Yeah, it's been many. Wow.
Is it A over S minus R?
Wow, that was, yeah, really good. It's if the sum is written like this, then this sum will converge to A first term over 1 minus R. Wow, nice memory, man.
Thanks.
Good job. But again, if this sum started at 3, then you'd plug in the 3, and that's what would go up here. So like this, I told you before, is just the first term in whatever sum you were given. It's not always just whatever number is here, because if it starts at a weird spot, then it won't be this A. Cool. Okay, then the nth term test, this is the one that says for any series in the world, if the limit to infinity of the terms isn't 0, then what has to happen?
Diverge.
Yeah, for sure it has to diverge. But you probably remember that, well, you can probably fill this in. This test can't tell you if the series converges. It can only tell you if it diverges. So if the limit is 0, that does not mean that the series will converge. It just means it might, like it has a chance. So it can't tell you if the series converges. Okay. Then the next thing you learned is the integral test, which says basically that if you have a sum, that it will converge if and only if the corresponding integral converges. And you can only use that if f of x is 3 things. Do you guys remember the 3 things? You can only use the integral test if that function fulfills 3 requirements. Remember?
Like continuous, decreasing,
nice. Yeah, continuous and decreasing, and what did you just say?
Positive.
Yeah, nice. Continuous, decreasing, and positive. Those are the 3 requirements. Nice, y'all. Okay, then P series test, when do these, well, it says any series of the form 1 over n to the P is called a P series. And that converges if something happens and diverges if something happens. Do you guys remember the requirement?
It
Nice.
converges if P is less than 1 and diverges if P is greater than 1.
Yeah, well, right number, but you said it backwards. Because you'd want a big power to make this really small. So P big, then converges if P is bigger than 1 and diverges if P is less than or equal. And then remember, if P is exactly 1, then that's called the harmonic series, and it diverges. Even though it looks like it should converge, it doesn't. Cool! Okay, hopefully these are coming back to you. Then we learned the direct comparison test, which basically says, like that if you have two series, and you have a series that you were given, and you know that it's smaller than a convergent series already, then remember the picture I made looks like this. I'm like drawing the terms of a series. Say those are the terms of a series, and you got a purple series and a red series. Okay. The thing that the direct comparison test said basically is that if you were given this red series and you know that this bigger purple series converges, then there's no way that the red one could diverge because it's smaller than a convergent one. So this says if your series is less than, let me make it like this. Let me make that red. If the red series is smaller than the purple series and the purple series converges, then of course the red series will also converge. That one is a simple idea, but it's hard to explain it, like convey what it's saying. But hopefully I did an okay job. And then it also says in the opposite direction. If now, let's say, reverse it. If your given red series is bigger, wait a series. Sorry. I still want this to be red, don't I? No, I don't. Sorry. If you were given this purple one, and you know it's bigger than that red one, and you know the red one diverged, then of course there's no way that the bigger one could converge. If the red one would be infinite, then the purple one would have to be infinite too. So like I said, hard to explain, but hopefully you're not too confused. If purple is bigger than red and red diverges, then the purple one has to also diverge. Okay. All right. That's direct comparison test. On the back, you got limit comparison test, which basically you can use if the direct comparison test isn't super obvious or it like doesn't work the way you want. Like if your red one is smaller than your purple one or whatever, but you need it to be bigger, then you can use the limit comparison test. In fact, remember the limit comparison test always works, whereas the direct doesn't always work. But the limit comparison test says the following. You take two series that you want to compare, just like the direct comparison test. But now you just take the ratio of them and take the limit to infinity to see which one is growing faster or if they're growing at the same rate. And this one is tricky, but as long as you get any number for the limit, like 2, 7, 8, whatever, 1/2, 1/3, whatever. If you get any number where L is not 0 nor infinity, basically, then both series will act the same way. In other words, they are growing at the same rate. So if one of them diverges, and so does the other one, and vice versa. Then this says if L is 0 or infinity, then the limit comparison test is inconclusive. So you probably chose some wrong, like the wrong series to compare your original series to if you get 0 or infinity. like try a different series to compare it to. Okay, that's up to 10.3. And we've done up to 10.5, so we only have a couple more. Watch this. 10.4 was alternating series test. This is the one that, like, of course, alternated between plus and minus, etc. And this one, I think I could ask you guys. Do you guys remember when this converges? Let me see how these blanks are laid out. This is convergent if a sub n is that for all n, if a sub n is a that type of sequence, and if the limit to infinity is something. You guys know what goes in these ones? What goes in this one? Yeah, it would be. These are
Positive.
specific. Wow, hey, great job. Yeah, you need 3 things to happen for this. Really, the big one is this one. But formally, you need to check 3 things. First, that the series without the alternating bit is positive. That's this first one. Then do you know what this second one means? The hint is over here, that the next term is smaller than the current term. Okay, yeah, this one is saying that the sequence has to be decreasing, which is what this means. Next term has to be smaller than the current. And then you should probably remember that this last one, that's the big one. What should the limit of the series be, or of the sequence? Well, maybe you don't remember. But for sure, the terms have to go to 0. Otherwise, it has no chance of converging. So this one is like the least strict that needs to happen. Basically, as long as your limit is 0, then your thing is going to converge if it's alternating. As long as these 2 things are met, which most of the time they are. All right, that was 10.4. And then finally 10.5, the last thing you learned. We don't have to worry about this yet. Not yet. This is what we're learning today, later. But the ratio test, this is one where you take the next term over the current term, and if the limit is less than 1, then it converges. If the limit is greater than 1, then the series diverges. And if it's exactly equal to 1, then you can't use the test. But that rarely happens. Okay, so is it a lot of things you've learned? Yes, but at least now you have it in one place and you can look through it. And a lot of them have to do with the number 1. Sometimes it's like if the limit is 0, or sometimes it's like if it's any limit. But most of the time, most of these tests have to do with, well, a lot of them have to do with the number 1. Okay, questions? All right, hopefully it came back to you a little bit. Now, bear with me as I talk to you about 10.6. So now get out your packets, but I don't think I want to get into your packets straight up. Because your packet just goes straight into it says, like, here's kind of an idea. Here it is. This paragraph basically says that there are some functions that are easier to work with than others. Like polynomial functions are easier to work with than other types of functions. And then it goes straight into an example. Here's something, and then there's an example. And it can be a little bit confusing if you just see the formula, like you have no idea what's going on. So bear with me as I try to explain it, because if you understand it, then you can derive this yourself. Whereas if you don't understand it, then you're going to have to be memorizing that, and that's hard to do. So watch this. First, let me convince you. Okay. There's 2 functions. You tell me, oh, the people in the video can't see, sorry. But I wrote 2 functions on the board. It's e of the x function and a polynomial function. And now let me ask you guys, if you had no calculator, which one would you rather plug the number 2 into?
X.
Yeah, for sure the polynomial one, g of x. And kind of interesting thing is that your computer would also rather plug things into the polynomial rather than the e to the x function. For whatever I don't know any computer science, but for whatever reason they tend to like polynomials are easy for them to work with, whereas other types of functions are harder to work with. So the idea behind this is that the idea behind what I'm about to teach you today is to use polynomials to approximate harder functions. So let me get something set up and tell you the idea. People in the video can see what I'm saying. Okay, watch this. If I was trying to approximate, I'm using e to the x because this is like the classic one, easiest one to start with. If I wanted to take e to the x and approximate it with a polynomial, I don't know how to make the people in the video see, so you guys may just miss out on some stuff that I'm writing, but hopefully it makes sense as I talk. But let's say I wanted to approximate this red function with a polynomial function. One thing I could do if I want it to be really, really, really simple is I could say, well, you know what I can do is I can just make sure that my function that I'm using to approximate matches the value of this red function at a specific point. So the easiest way to start is to say, okay, my function, g of x, when x is 0, I'm just choosing 0 because it's an easy point to start with. Like you could start anywhere arbitrarily, but I'm going to match this value 0, 1. So the easiest function I can think of that goes to the point 0, 1 is this constant function g of x equals 1. So let me see how good that does at approximating this. Okay, there's my approximation in blue. Here's the original function in red. You can see, yes, it does match it at one point, but everywhere else it's pretty far off, obviously. Okay, so this is a bad approximation. How could I make it better? Oh, idea. What if instead of just matching the function value at 0, I matched the function value and the slope, like the derivative value? Yeah? Okay, so here's some side work off to the side here. If I wanted the slope to also match there, then I would need the derivative to be the same.
Maybe it's get to add up.
So hopefully you remember after spring break that the derivative of e to the x is e to the x, yes?
Yeah.
So therefore the derivative of f prime of 0 equals e to the 0, which hopefully you remember is 1. Okay, so you give me a simple polynomial function whose derivative is 1. Yeah, okay, so why don't I just add an x to this? Watch this. Okay, and now my my approximation is a little bit better. In fact, it's really, really, really good right by the point that I'm interested in, the point 0. Very, very close between the blue and the red, but everywhere else it's pretty far off. Agreed? Okay, notice this was not a coincidence, but notice that I didn't ruin the previous thing. Like, what I mean is, I'm still touching at the point 0, 1, like the function still goes to the point 0, 1, and it has derivative, the derivative that I want. This will be clear what I mean in a second when we do a second degree thing, but I thought I should mention it. Okay, now let me speed up because now you're getting the idea. The blue does a decent job, but what if I went even further? What if I matched not just the function value and the derivative value, but also the second derivative value? So it would match the value, the slope, and the rate of change of the slope. Okay, so here's me speeding up a little bit. If I now want to match the second derivative, then I would want the second derivative to be, give me a sec. I'd want the second derivative to match the second derivative of my function. So the second derivative is still e to the x, and f double prime of 0 is still 1. Okay, so now back to you guys. Can you think of a simple polynomial function whose second derivative is 1.
I guess it's that one right there.
Well, maybe I gave it away. Yeah, but okay, if I need a second derivative in this thing, like notice if I just took the second derivative of g as it is, then I would get 0 for this term, 1 for that term, that's my first derivative, and then second derivative would be 0. So I need to add an x squared term in here so that the second derivative is even like non-zero. You know what I mean? So for sure I need an x squared term in there. Oh, that's a C. Okay, for sure I need an x squared term in there. But now when I take the second derivative, watch this, let me do it down here and then erase it in a second. I would get, here's my first derivative, 0 plus 1 plus 2x, and now my second derivative would be 0 plus 0 plus 2. So I don't want it to be 2, I wanted it to be 1. So I need to divide that by 2. Yeah, exactly. That's why I'm divided by 2. Okay. Oh. There. Cool, and now you can see the blue matches it farther along than the tangent line did, which is neat. Okay, cool, and you can guess that if the more terms you keep adding, the closer and closer it's going to match. So let me do one more with you guys before you guys get bored. Now I want to match the function value, the first derivative, the second derivative, and the third derivative. And hopefully you guys can see ahead that the third derivative of this red function will be what?
X to the 3 over 3.
Well, hang on, of the red one, of the e to the x.
E to the x.
Yeah, e to the x, and then you plug in 0, and you need it to be, the derivative to be 1. Okay, so now you're thinking, okay, I need to add another term to this so that the third derivative even exists, and I need that third derivative to be 1. So what did you say that should be?
X to 3 over 3.
X cubed over 3. Nice. Okay, let me check with the work that I already had. So 0 plus 1 plus 2x over 2 now, over 2. Plus, okay, derivative of this would be 3x squared over 3, which is just x squared. And then the second derivative would now be 2x, and now the third derivative would be, 0 plus 0 plus 0 plus 2. Rats.
Put it over 6.
That's what you need to do, is put this not over 3, but over 3 to cancel this 3, and over 2 to cancel that 2. So over 3 times 2, over 3 times 2, over 2, over 2.
So it's just factorials, pretty much.
Hey, nice. That's where those factorials are coming from on that poster. So now watch this. Boom, and now it's matching it really, really close. Okay, you guys with me? It's still making sense. Cool, okay. And notice, let me bring back the thing I was going to say before. Notice that you didn't ruin any of the previous derivatives. Like, for example, we needed the first derivative to be 1 still, and now we added all these terms that maybe we messed something up, like with the previous derivative. But since we're taking all these first derivatives at 0, all these x's that are like left over right here, well, you're going to plug 0 into anyway. So your first derivative is still going to be 1. You see what I'm saying? Second derivative will still be 1, etc. Cool. All right. Well, there's the idea. I'll ask you about one more term after this question.
So then you basically, it's like you just do the series of whatever. Like we're going to be making series of those for each one.
Nice. Yes, exactly. Yeah. Yeah, so Sam sees ahead. He's like, okay, this is getting better and better and better and better and better. Of course, the more terms I add, the closer the blue will match the green. So first of all, let me ask you, the next term would be what to match the fourth derivative?
X to the 4 over 24.
That's the 4 over, nice, 24 being 4 factorial. 4 times 3 times 2 times 1 to cancel each of the powers that you get when you take a derivative. Okay, so over 24, and now look how good that is. And then so on and so on and so on. You get better and better approximation. And so Sam is saying, oh, you know what would make this really, really good? If instead of going to 5, I went to infinity. And that's what's coming up. In fact, that's what you see if you're in the room and not on the video. That's what you see up there in that poster. is a bunch of series to infinity that approximate e to the x, or not even approximate it, because if you go in like an infinite number of terms, then you get exactly the function e to the x. Cool. Okay. I just said a lot of words, but like I said, I think it's more important to understand that than to try to memorize. This formula on your thing. Like that would make no sense to me as a student. It's still like if I look at it, it's still overwhelming. I have to think about what you're actually doing. So hopefully, if you forget the formula on May 11th, you can like derive it yourself real quick. Like, oh yeah, I want to match derivatives and second derivatives and all that. Cool. Okay. Let's do one or two examples, and then just so we have something written on our thing, and then we'll be done for today, and we'll finish this tomorrow, and then 10-7 Thursday because I have a meeting Wednesday, and then 10-8 Friday, and then we'll be done with curriculum, I hope. Okay. It says write the Taylor polynomial of degree 3 centered at 2 for the differentiable function f such that stuff happens. Okay. So first of all, I forgot to say that this idea of matching, approximating a function using a polynomial, that's called a Taylor polynomial. Notice that I used the point 0 to center my polynomial at, like matching all the function value, first derivative, second derivative, matching all those values at 0. This question is asking about matching all these functions. This function is asking about matching all the values at 2 instead of at 0. So all you're going to do is, let me try to make this for the people on the video. All you're going to do, instead of centering this at 0, is you'll just shift all these x's over by 2. So all of these would look like x minus 2 here, x minus 2 here. And now it's not going to look anything like this red function, but I'm just trying to show you this is what you do if you were trying to shift any function over by 2, is subtract 2 from each x. Like, that's what our thing will look like. So that's why on your thing, on your little packet, these x minus c's are there. This is like wherever you want to center it.
Does that mean that 1 changes to like whatever, e to the 2?
Yeah, exactly. That's why the blue didn't match the red anymore once I shifted it over, is because now you'd have to change the values in front. But yeah, that's what you're gonna do. Okay. And then one more thing, just so we're all on the same page, like on the vocab, if your center is not 0, then that's what's called a Taylor polynomial or a Taylor series. And if it is centered at 0, like we did with our example, then that's called a Maclaurin polynomial. That's the only difference. Okay, so Maclaurin is just a specific case of the Taylor polynomial. Okay, now example, and then we'll be done. It says write the Taylor polynomial for this of degree 3 centered at 2. Okay, so you would want to match the function value, the first derivative, etc. And remember, you want to divide out by all the powers that you're taking. So the way I write this is polynomial of degree 3 of x would equal, okay, and then I want to match the function value, so it would be 3, no x's in there, plus the derivative value, so minus 4 times x minus 2. It might be easier to write it first and then like convince you later. And then plus 7, and also you can just look up here and try to match this. So plus 7 times x minus 2 squared, because that's my second degree polynomial. But don't forget that you got to divide out by that 2 that's going to be there when you take derivative. So divided by 2. Or if you really want to match the little box, you can make it a 2 factorial. But 2 factorial is 2. And then finally, third term, minus 5 times x minus 2 cubed over 3 factorial. If you really wanted to, you could put a 1 here and a 1 factorial, and and a 0 here and a 0 back here. But okay. Okay, so again, look at up here in our example, all of these were 1s because all our derivatives were 1s. So all of these coefficients were 1s. But whatever you, whatever your derivative is, that's what your coefficient for that term will be. So first, my first derivative here was -4. That's why my first coefficient on my first degree term was -4. Now I may have made it more confusing. Let me delete all that. Question.
Is that like P3X, like the formal notation? Like that's how you should write it on the test?
Yeah. Yeah, that's pretty well standard. Other questions? What time is it? 40. Okay, then maybe this would be good to come back to tomorrow because you guys just got a ton of information. So yeah, we'll do the rest of these tomorrow, and we'll see if we maybe we can. If we could start 10-7, that would be really good. I don't want to bleed into next week.
Like, keep a meeting on Thursday too?
No.